We're going to discuss maximum values of polynomials. We're going to use a sheet of paper to discuss the largest possible volume that we can get from that sheet of paper by folding up the sides, cutting out the corners, and creating a box that does not have a lid. So what you do is you take the piece of paper, I just used a regular 8.5 by 11 piece of paper, and you fold up the sides. You do the left and the right the same as the bottom and the top. So I did just a few examples so you can see the difference between them. With the red paper, I folded up all the sides 1/2 of an inch. The orange paper was 1 inch. The yellow paper was 2 inches. The blue paper was 3 inches. And the pink paper was 4 inches. Now I couldn't go any bigger than technically just under 4¼ inches, because you can't take off 5 inches from the left and 5 inches from the right when you only have 8.5 inches to begin with. So when we talk about restricting the parameter of an equation, that is what it means. We just go with the practical sense of it's 8.5 inches wide, so the amount that you cut off has to be less than half of that. So if you look at these, the 1/2 of an inch one, the red one, is really, really small. The area is very large, but the height is very small. And remember, we want the largest possible volume, and the volume of a rectangular prism is length times width times height. So the orange one has a little bit better height, and the area is just a teeny tiny bit smaller. And then the yellow one has a higher height, and the area is a little smaller. The blue one, the area is a little smaller. And the pink one, the area of the base is very, very small. It's almost non-existent. And that was the one that we took 4 inches off of each side. So which one do you think is going to have the largest possible volume? The question is, what size of squares should we cut out of the corners to get the largest possible volume? And mathematically, a lot of times the question is also, what is that largest possible volume? So make your guess which one of those has the largest volume. Use the area of the base times the height to make your guess. It might help if you look at the bottom of the table where you have all those pieces of paper that were cut out. That's what's missing. And then now look at the boxes after they are folded up and then taped together so they actually make a rectangular prism. Which of those has the largest possible volume? Then we calculate. So we know the height of each one. That's the size of the square that was cut out. So the red one had 1/2 inch by 1/2 inch square cut out. The orange one had 1 inch by 1 inch square cut out. The yellow had 2 by 2 inch. Blue was 3 by 3 inches. And then the pink one was 4 by 4 inches. This is an 8.5 by 11 piece of paper. So originally it was a length of 11 inches. Well, when you take 1/2 inch off the bottom and 1/2 inch off the top, we get the 10 inches for the length. When you take 1/2 inch off the left and 1/2 inch off the right, then we get 7.5 for the width. So then you do that for each paper. So you take off the height of the box twice for the length, and then twice for the width. So you get the length and the width of each paper, and the length times the width times the height gives us the volume. So then we compare the volumes of each piece of paper. Here we can compare the different volumes of the papers, and here I plotted the x value as the height of the prism and the y value is the volume of the prism. So you can see as the height increases, the volume increases, and then as the height continues to increase, the volume starts to decrease. And we don't want to do all that math every single time. We want to come up with an equation to figure out the best size of square to cut out. So the volume is length times width times height. Then we need to fold up the sides an arbitrary length. We call that x. So the new length is 11 minus x, and the new width is 8.5 minus x minus x. So we cut the corners out, and then we take the sides that are left and fold those up. And that's what makes the height of the box, or the borders around the box. Now the inside rectangle, that's your base. And then here you look at what I have drawn black. that is what you fold up. And then if you look at what's brown, that's the actual height of the new prism. And so x is the height of the prism. And then the 11 minus 2x is the length. The 8.5 minus 2x is the width. And so that's what you type into a graphing calculator, and you graph this polynomial, and the y values we see right there are the possible volumes of the box. And so we want the highest volume. Well, this is where we find the relative maximum, and you just figure out that ordered pair right there. Remember, x was the height, and the y value is the volume. So when you make a box out of a regular 8.5 by 11 piece of paper, the largest possible volume is 66.148 cubic inches, and we get that by cutting out squares from each corner that are 1.5 inches by 1.5 inches. This one's actually 1.585 inches. You use that same kind of equation for other sizes of paper. If you did a 3 by 5 note card, you would have 5 minus 2x and 3 minus 2x. If you do an 11 by 17 piece of paper, you're going to do 17 minus 2x and 11 minus 2x. Just remember to have the length and the width and the height.